Hello and welcome to Precalculus lesson number 30. In this video, we're going to learn about systems of linear equations. Linear equations in n variables. The definition of a linear equation in one variable that we have seen before can be extended to more than one variable. An equation of the form a1 x1 plus a2 x2 plus plus an xn equals b, where the coefficients are real numbers and non-zero, is called a linear equation, meaning first degree equation basically in n unknowns. Next, we want to talk about systems of linear equations. Solving some real-life problems necessitates that a group of equations be solved simultaneously to determine a desired outcome. Such a group of equations that must be solved simultaneously is called a system of equations. If all the equations of the system happen to be linear, then the system is called a system of linear equations. A solution of a system of equations must satisfy every equation in the system, whether the system is linear or not. Now, if we bring our attention just to a system of two linear equations in two unknowns, then geometrically speaking, such a system is going to fall into one of these three categories, okay? Basically, a solution of such a system should be a point of intersection, right, of the lines involved, because that would be the point that would satisfy both equations, right? So that's the geometric interpretation of the solution. Notice that when it comes to two lines in the plane, only one of three scenarios can occur. Either they meet exactly at one point, such as this graph, or they meet at every point. Notice these two lines are basically coinciding, so their equations would be equivalent. They may look different if they're not in slope-intercept form, but once you put them in slope-intercept form, they'll be identical. Or there'll be this last scenario where they don't meet at all. In other words, the lines are parallel. Now, notice that for the first scenario, the two lines, because they have a solution, the system would be called consistent. And given that they're different lines, that this being a solution of one of these two equations doesn't necessitate also being a solution of the other at the same time. So therefore, we call such a system independent. So this would be a consistent and independent system. For this scenario, notice that being a solution of one of these equations is going to necessitate being a solution of the other as well. So that's why such systems are called dependent systems. But obviously, the system has more than even one solution. All it takes is having one solution to be called consistent. Given that it has infinitely many solutions, it's definitely consistent. So this kind of a system is called consistent and dependent. Notice that, as I said, even if they look different in other forms because of being multiplied by some coefficient, once they're put in slope-intercept form, they should be identical. The slopes should be the same, and their y-intercepts should be the same. With the first case, all we can tell is that their slopes are different. That's all you need to know in order to know that a pair of lines is going to meet at only one point, at exactly one point, as long as the slopes are different. Now, the y-intercepts may or may not be the same. For example, in this scenario here, the y-intercepts are different, obviously, right? They cross the y-axis at the same time. But maybe the two lines intersect exactly on the y-axis. In that case, the y-intercepts would be the same. But again, the y-intercepts don't matter. As long as you know that the slopes are different, you know the two lines are going to meet at one point. Now, in this scenario, once you put the two equations into slope-intercept form, what's going to be happening is that because they're parallel, their slopes should be the same and will be the same. But because they're different lines, they are not going to be like this scenario where both are going to meet the y-axis at the same point. In fact, their y-intercept should definitely be different. And as you can see, they are different here, okay? B1 and B2 are not the same. So that is the telltale sign. So because this system, this last one, has no solution, we call it an inconsistent system. But because the two lines are distinct, and the solution being a solution of one doesn't necessitate being a solution of the other as well, it is an independent system. So this last type is called an inconsistent and independent system. All right, so we're going to solve this particular system of equations using the substitution method, and we're going to determine the consistency and dependency status of the system, also state the number of solutions of the system. Now, this kind of a system where obviously one variable is solved in terms of the other is an ideal candidate for the substitution method, because we're going to basically, using the substitution method, solve one of the equations for one of the variables in terms of the other variable in one of the equations, and then substitute in the other equation. Now this one already has done that for us. So all we're going to do is we're going to substitute the y in the first equation with 3x, which we know is the y from the second equation. So we get 5x plus 3x equals 16. So 8x equals 16. So x equals 2. We divide both sides by 8, right? So now all we have to do is go ahead and substitute this 2 for x in either equation. Obviously, this is a much simpler one to use, so that's what we'll use. So we get 3 times 2. So we get y equals 6. Do note that if I had plugged it into the other one, so 5 times 2 plus y equals 16, so I get 10 plus y equals 16, or y equals 6. I would have obtained the same y value, because obviously this is a point of intersection, so it should satisfy both equations, right? So the ordered pair, now we always want to present the solution in the form of an ordered pair. You always put the x first and then the y. So the ordered pair is going to be 2, 6. Now you can quickly see that this ordered pair satisfies both of these equations. So plugging into the first one, you get 5 times 2 plus y is 6. So 6, we want to know if that's equal to 16. So 10 plus 6, is that equal to 16? Yes, it is. 16 equals 16. We can now drop the question mark. We've verified it. In the second equation, we want to know if y, which is 6, is equal to 3 times x, which is 2. And 6 does equal 6, so that's checked out as well. So to check whether a solution you have found is indeed the correct one, you want to substitute it into both equations, or if you have more than 2 equations, into all equations, and make sure that it satisfies all of them. That's how you verify the solution for a system of equations that have to be solved simultaneously. All right, so this is one of the scenarios where two lines are intersecting at exactly one point. So this system is obviously consistent because it has a solution. And since the two lines are distinct, this is going to be an independent. So this is a consistent and independent system. As far as the number of solutions, make sure you understand that even though you have a pair of numbers, the ordered pair is considered just one point of intersection, so just one solution. Okay? That's how you handle that. We're going to solve this next system using the same method, substitution. So as long as you have at least one equation where one of the coefficients, either x or y, is 1, that system is a good candidate for the substitution system, because it's easy to solve for one of the variables in terms of the other. For example, in this one, if I go ahead and solve for x in terms of y, I get x equals 4 minus y. Then I'm going to take this 4 minus y and substitute it for x in the other equation. So I get 4y equals 3 times 4 minus y plus 16. So we get 4y equals 12 minus 3y plus 16, right? So 4y plus 3y equals 28. So we get 7y equals 28. So we get y equals 28 divided by 7, which is 4. Remember, you can take this now and plug it into either equation or even a modified equation as long as it's been done correctly. This obviously is the perfect equation to plug the 4 in, because that quickly tells you what x is. So x is going to be 4 minus 4 or 0. So the solution set is going to be contain the ordered pair 0, always x first, and then y. Sometimes the students make the mistake of plugging whatever they find first, and then whatever they find second in the second spot, but you know better than that, right? This is always in the form of x comma y. All right, and that's how we do that particular system. Again, because there's only one solution, that indicates this should be two distinct lines, right? And so therefore, because there's a solution, it's consistent, and because they're distinct lines, it's going to be an independent system. I leave it as an exercise for you to check that solution in both of those equations. But I do want to take the time to show you one other thing. First of all, the number of solutions will obviously once again be 1. Now, notice one thing, that if you were to put both of them into slope-intercept form, watch what happens. So the first one is 4y. By the way, we are finished, okay? This is just a little extra side note for better understanding. So notice, to put this in slope-intercept form, I would have to divide by 4, right? So I get y equals 3/4 x plus 4, correct? Now, putting the other equation into slope-intercept form, I get y equals negative x plus 4. Now, remember, the only requirement we have for having the first type of system, the consistent and independent system, is that the slopes should be different. And notice here, m1 here is 3/4, m2 here is negative 1. Whether the y-intercepts happen to be the same or not is not important at all. What's important is that m1 does not equal to m2. As soon as you see that the slopes are not the same, you know for sure that these two lines are going to, well, the two lines associated with these equations are going to intersect at exactly one point, okay? All right, so in this system, we notice neither of the equations has a term where the coefficient of either x or y is 1. So this system is very, very suitable for another method of solving, which is elimination. Basically, we're going to try to get the same coefficient for x or for y, and then combine the two equations to eliminate that variable. We notice here that x would be a very, very easy variable to work with, because all I need to do to eliminate x is multiply the top equation by -2. Notice we end up with negative 8x minus 6y equals -6. And this one we don't change, we just bring it over. So 8x minus 5y equals 39. So now notice we can go ahead and combine the two equations by adding, and that's going to eliminate the negative 8x and 8x, and here I get negative 11y equals 33. Now we can divide both sides by negative 11 to get y equals negative 3. So now we can take that and plug it into either equation. I'll just go with the top one because the numbers are a little bit smaller, so it'll be a little bit easier. So 4x plus 3, and I'm substituting negative 3 for y. So there's still a little bit of substitution involved, but that's at the very end. So we get 4x minus 9 equals 3. So 4x equals 3 plus 9, or 4x equals 12, so x equals 3. So the solution set would be the ordered pair 3, negative 3. I leave it for you to check that because otherwise our video would be way too long. And I do want you to notice that the system is consistent and independent. Now, I do want to demonstrate the fact about the slopes again by putting them in a slope-intercept form. So yes, I'll save you some time on checking, but you know I'm going to use it for something else. All right, so the first equation, if I move the 4x to the other side, becomes this, right? The second equation is negative 5y equals negative 8x plus 39, right? Now I'll divide both sides of the first equation by 3 and both sides of the second equation by negative 5, right? So notice you end up with negative 4/3 x plus 1 for the first equation. For the second equation, we get y equals positive 8/5 x and then minus 39 over 5. Do notice that M1 is different from M2, so it's consistent with what we are describing here. The number of solutions, once again, 1. Okay? All right, let's go ahead and solve this one, which has some fractions in it, but not to worry. The great thing about equations is that you can eliminate fractions first, and as you know, multiplying both sides of an equation by a constant doesn't change the solutions of the system. Look at this simple example. X plus 2 equals 3, right? Now, we know the solution to this system is what? X equals 3 minus 2, so it's 1, right? Now, let's say I were to multiply that equation, both sides of that equation, by 3. I would get 3x plus 6 equals what? 9. So I would get 3x equals 9 minus 6. So I would get 3x equals 3 or x equals 1. Notice, multiplying both sides of an equation by the same constant, here we multiplied by 3, for instance, right? Does not change the solutions of the original equation. And that's the reason, that's why we can get away with doing this, right? Okay, so let me go ahead and clear all that. All right, so that's what we're going to do. We're going to multiply the top equation by the LCD of all its denominators, which is just 6, right? The denominators are 2, 3, and 6, so the LCD is just 6, and we end up with, let's see, don't forget, we're multiplying each of these terms by 6, right? So here we're going to get a 3 on the top. Here we're going to end up with a 2 on the top, and these will clear completely, right? So we end up with 5x times 3 becomes 15x plus 10y equals 155. And down here, the LCD is 12. So again, remember that we're multiplying all the terms on this one by 12 because of distribution, right? On the first one, the 4 and 12 leave us a 3. On the second term, 3 and 12 leave us a 4 on the top, and the 12s cancel completely on the other side. So we end up with 3x plus 4y is equal to 35. Now that's much simpler to work with, right? Now, if you really want to take advantage of smaller numbers, you could also, before you proceed with elimination, you could also divide both sides of this by 5, but that almost like is not worth it, so we won't do that. Let's go ahead and eliminate x. It's easier. We just need to multiply one of the equations by a number, which is like -5, right? The first one we will leave alone. So we have 15x plus 10y equals 155. And down below we now have, remember, we're multiplying both sides of this equation by -5. So we get -15x minus 20y. Make sure you multiply by all those terms. And on this side we have, let's see, 150 and 25 gives us 175, so -175. All right, so these cancel out obviously, and we end up with -10y equals -20, right? So what's y? 2, right? So now we can take the y equals 2, plug it into one of those, or better yet, we'll plug it into one of these. And this is the one with the smaller coefficient, so we'll go there. So 3x plus 4, remember, we're substituting this 2 here. 4 times 2 equals 35. So 3x plus 8 equals 35. So 3x equals 35 minus 8, which is 27. So x equals 9. We write the ordered pair for the solution set, which is 9, 2. Check the ordered pair for your own sake. So the number of solutions here is 1. The system, once again, is consistent because it has at least one solution, and independent because they're obviously distinct lines. Otherwise we'd have what? Infinitely many solutions, right? And that's how you would approach that one. Okay, make sure you can carry that on your own. We will move on. Okay, so we're going to go ahead and solve this system. Now it looks like either variable is easy to eliminate. I'll just go ahead and eliminate, say, y. Okay, multiply the second equation by 4. First equation I will leave alone. So notice what happens. You don't end up just eliminating y, you eliminate x2, but you're not left with nothing, you're left with a 0, okay? On that side, however, we're adding the two equations. I end up with 40. Now this is a contradiction. So what does that tell me? That means I was trying to do the impossible. I was trying to find the point of interception. Let's try that again. The point of intersection for two parallel lines is what's happening here. Okay, so this is when we know there's not going to be any solution. So no solution. So the number of solutions is 0, okay? And the system does not have a solution, so it's inconsistent. We call that, we use that name for systems that have no solution, and they're obviously not coinciding lines, they're distinct lines, so the solutions of one does not depend on the solutions of the other, so it's an independent system. So it's an inconsistent and independent system. Now I do want you to take a look at the slope-intercept form of these two equations because it will tell you much. The first one, I'm going to keep the negative 4y on the left, move the 12x to the other side, becomes negative 12x plus 20. On the second one, keep the y and move the negative 3x to the other side, so you get 3x plus 5. So I still need to divide both sides of the first equation by negative 4. So I get y equals 3x minus 5. The second one is finished. I'm just going to rewrite it. So let's go back to that classification page real quickly. So note that for these inconsistent and independent systems, the slopes are going to be the same because they are parallel after all, but the y-intercepts will be different. Now, if we go back to our example, you'll see that that's the exact scenario that we have. Notice that in slope-intercept form, these two equations have the same slope. The m is the same, but they have different y-intercepts. As I said, this is the telltale sign of an inconsistent and independent system once you put them in slope-intercept form. Please make sure to understand that, and we'll proceed. All right, let's go ahead and try to solve this system by elimination. And I notice I can go ahead and eliminate x quickly by multiplying the top equation by 2. And I end up with 6x minus 8y equals 2. The second equation we'll leave alone, negative 6x plus 8y equals negative 2. We go ahead and add the two equations, and this time, like the previous time, both terms are going to zero out, so we end up with 0 on the left side. But unlike the last case, we also end up with a 0 on the right side. Now, this is not only not a contradiction, it's as far away from a contradiction as it can be. It's an identity. Now, what does that indicate? That indicates these are basically two equations that are only superficially different. If you take one and multiply it by a constant, you get the other. In this case, I wasn't trying to get the other, I was trying to eliminate. But if I take the first equation and multiply it by negative 2, watch. I get negative 6x plus 8y equals negative 2, which is exactly the second equation. So when one equation is just a constant multiple of the other, remember, equations that are constant multiples of each other have the same solutions. That means being a solution of one of these two equations is going to necessitate being also a solution of the other equation. That's why this is the kind of system which we call dependent. And of course, such systems are not only going to have one, but rather infinitely many solutions. So because of that, they're also consistent, because remember, consistency means having solutions. So this is a consistent and dependent system. And basically, it's representing a pair of coinciding lines when you graph it, right, geometrically speaking. All right, and do notice that if you take the two equations, and put them both in slope-intercept form. For the first one, I'll leave the negative 4y on the left side, move the 3x to the right side, becomes negative 3x plus 1. For the second one, I'll leave the 8y, and I'll move the negative 6x to the right side, becomes 6x minus 2. For the top equation, I will now divide by negative 4 both sides, so I end up with y equals positive 3/4 x minus 1/4, right? And the second equation will divide both sides by 8. We end up with y equals 6/8, which remember is the same as 3/4, so 3/4 x, and then minus 2/8, which as you know is the same as 1/4. See what happens? Once you put them in slope-intercept form, any superficial difference between them goes away, and the equations end up being identical. Notice that m1 is equal to m2 and b1 equals b2. That's the telltale sign of a consistent and dependent system. All right, so that's how you handle those. The only thing left is writing the solution system. Now, there are two ways you can write the solution system. Basically, take one of the equations. You can solve it either for x. Let me move it up a little bit. You can solve that either for x or y. Let's say we solve for x. We get 3x equals 4y plus 1, or x equals 4y plus 1 over 3, right? Or I could have solved it for y. So in that case, I would get 3x minus 1 equals 4y. I'm moving the negative 4y to the other side. So I get y equals 3x minus 1 over 4. So one way I could represent the solution set is like this. I could say it's all ordered pairs of the form x, comma, we go to the one where we solve for y, so 3x minus 1 over 4. That's one way. Or I could have represented the solution set using y's. Okay, if I use y, then my x would be 4y plus 1 over 3. So both of those are proper ways of presenting the solution set for this system with infinitely many solutions. So sometimes they will specify if they want you to use x in the solution set or y. So just be aware of that. Now you may be thinking, what do you mean infinitely many solutions? Well, easy. If I take, let me open up some space here. All right, everything is there. I just shrunk them and move them over a little bit. If I, let me erase that. All right, let's say, because sometimes students, they hear, oh, infinitely many solutions, and they're given something like this, and then somebody says, can you generate like 3 solutions for me? And they won't be able to do it. But this is very easy, remember? So for example, let's say I'm using this description with the x, right? Using x. So all you got to do is, for example, let x be 1, okay? Then solve for y. So y is going to be 3 times 1, which is 3, minus 1, which is 2 over 4. So 2 over 4, which is the same as 1/2. So here's one solution. If you don't believe it, just plug it in, and you'll see that it should work. Plug in 1 for x, you get 3 times 1 is 3, minus 4 times 1/2, that becomes 2. 3 minus 2 is 1. Do the same in the other equation. You'll see that it works. So let's say they want you to make a custom solution where the y value is 5, right? Provide a solution with y equals 5. Now, if that's the case, you would be much better off using this version of the solution set, right? Then just go x, if y is 5, then x is going to be 4 times 5 plus 1 over 3, which is 21 over 3, which is 7. So here is another ordered pair that's a solution of this equation. Remember, 3 times 7 is 21, 4 times 5 is 20. What's 21 minus 21? Now, there's 2 examples, but if they just want you to generate 3 solutions with no custom description given, then just let x be 1, plug it in, get 1 solution. Let x be 2, plug it in, get another. Whatever value of x you like, plug it in here and get your y coordinate, and that's it. You have your different solutions. So that's what we mean when we say infinitely many solutions. There really are infinitely many solutions. You just have to basically find the ones that you need. Okay, and that's that. All right, next we want to find a system of equations that would actually have these lines as its representation. Now, this solution here is actually kind of put there to throw us off. We don't really need it, right? Notice that we know that this line right here, the blue one, goes through 0, 5. So the blue line goes through 0, 5, and 4, 0. So I know what the y-intercept for the blue line is, right? The b. Well, the y-coordinate of the y-intercept, b, is 5, right? And we can find the slope easily, just visually even. To get from this point to this point on the blue line, you have to go down 5, right? And then right 4. So the slope is -5 over 4, right? So we're ready to write the equation for the blue line. Y equals -5/4 x plus 5, right? Now, for the red line, I know the y-intercept. So for the red line, I know that it goes through 0, 2. The y-intercept is ordered pair 0, 2, which makes b 2. And I know I can find the slope easily too. Remember, always go from left to right. So to get from this point to that point, I would go up 2 and then to the right 4. So the slope for this one is what? 2 over 4, which is the same as what? 1/2. So now we're ready to write the equation for the red line as well, right? What is it? Y equals 1/2 x plus 2. Okay, so there's the system, except they want you to write the equation in standard form. So that means get the x's on one, and y's on one side and the number on the other side. So for the top line, I have 5/4 x plus y equals 5. So I'll go ahead and multiply both sides by 4 to get rid of the fraction, because that's the way we like it in standard form, right? So 5x plus 4y equals 20. For the second line, if I move the 1/2 x to the left, I get -1/2 x plus y equals 2. Since we usually like to have a positive lead coefficient, we'll multiply both sides by -2. On the top, we multiply it by 4. So we get x minus 2y equals -4. And there is our system in standard form. Okay, so yeah, this happens to be the solution, but notice we didn't use that at all. We didn't need it. We just needed to find the equations of the two lines from the graph. That's all. Okay, let's go ahead and move on. All right, next we want to go ahead and take a look at systems of three linear equations in three unknowns. Now, as you can imagine, when the number of variables goes up, the graphics becomes much more interesting. Linear equations in two variables are generalized by the form ax plus by equals c, if you recall, where a, b, and c are real constants and x and y are real variables. And they represent straight lines in two-dimensional Cartesian coordinate plane, as we have seen, right? And we know that two unique points in a plane determine a line. Now, that's pretty strong language. That means, basically, given two distinct points in a plane, there is one and only one line that will go through those 2 points, okay? Or we can say that contains those 2 points. Now, linear equations in three variables are generalized by this form, ax plus by plus cz equals d. And here a, b, c, and d are real constants, x, y, and z are real variables. And they can be represented as planes. Rather than lines, they turn into planes. Now remember, these planes, we're just showing you a little slice of them here. They go on forever in all four directions, right? So these are complete planes in three-dimensional Cartesian coordinate plane that you can see right here, where a point is no longer represented by just an ordered pair, but rather by an ordered triple, x, y, z, where, you know, the first one will be the coordinate along the x-axis, the second will be the coordinate along the y-axis that you have to go, and the third one will be the coordinate along the z-axis. Now, as it turns out, if you have three unique points in a plane, this they determine in space. I mean, three unique points in space. They're going to determine a single plane. Meaning, if you have three distinct points in space, there's one and only one plane containing all three of them. That's the equivalent of the fact that we said in a plane, if you have two distinct points, there's only one line that goes through them. So everything kind of carries over to an additional dimension. And this is the way that three planes in space can interact, right? Either the three planes are all going to coincide. We say all coincident. They're going to be basically the same plane. Or you may have two of them coinciding, like here P1 and P2, and then another one intersecting them. Or you could have two coinciding and the other one being parallel to them, in which case these will never meet at a single point or a line. Here you can see two parallel and one intersecting plane, right? Here's two parallel planes with one intersecting them. If you look at this as a system, this would have no solution either, because remember, a solution would have to satisfy all three equations at the same time, and there would be no point common to all three of these planes. So that system would not have a solution. This would not have a solution either, the one we already talked about. This would most clearly not have any solutions. The three lines are parallel. This is actually the most common one we're going to be solving, the one where they do actually meet at a single point, and the system is going to have one solution. Notice that we have this kind of possibility where the three planes meet at a line. See, they have a line of intersection possible. So this one would have infinitely many solutions, right? And here's another one where you have the line of intersection of any two is parallel to the third plane. Now, this system here that meets like this won't have a solution here either, because there is not a single point that exists on all three planes. So that would not have a solution either. Now, as I said, the type of the system most encountered in applications is type 6, where you got one single point in space, which is a solution of this form, right? Order triple. And that's basically what moving up a dimension is going to look like. Let's go ahead and look at some systems. All right, so here's a system of three equations and three unknowns. And the good news is you don't have to generate that graphic to be able to solve it. That's where algebra comes in. All right, so the way we're going to approach this is the following. We're going to do what we call system reduction, meaning we have three equations in three unknowns. We're going to try to see if we can get to two equations in two unknowns, because we can solve those, as you know. But we got to get all the equations involved, right? So the way we do that is very clever. We go ahead and, first of all, let me give these equations names for reference. So let's say we call the first one 1, the second one 2, and the third one 3. So what we will do is we will take one pair of equations, like let's say we take 1 and 2, right? And then we'll take another pair and we'll eliminate the same variable from those two pairs. So like let's say I can see z is a very easy variable to eliminate, because I can just add those two equations and eliminate z, and I can add these two, 2 and 3, and eliminate z. So that's what we'll do. We'll take 1 and 2 and eliminate z, and we'll take 2 and 3 and eliminate z, the same variable z, and we'll see what happens. Look, let's take 1, which is x plus y plus z equals 5, and 2, which is 2x plus y minus z equals -6. We'll go ahead and eliminate by adding. It's as simple as it gets. So we get what? We get 3x plus 2y equals -1, right? Now we'll do the same thing. So remember, this was 1 and 2, right? We have a new equation. Let's call it 4, okay? Now we'll do the same thing with 2 and 3. 2 is 2x plus y minus z equals -6. And 3 is x minus y plus z is equal to 9, right? So again, notice it's very easy to eliminate z. Just add the equations. So you end up with 3x. Now, in this case, we end up eliminating the y as well, right? So we get 3x. So both y and z eliminate. So we get 3x equals 3, right? Now, that's very fortunate, because that's just going to quickly give us what x is, right? Now we're going to take that. We're going to plug it in for x here. That'll give us y. So we get 3 plus 2y equals -1. So 2y equals -1 minus 3. 2y equals -4. So y equals -2. Now we have x and we have y. We're going to go ahead and plug it into any of the three equations and get z. I'll just go with the top one because it's nice and simple. So I have x plus y plus z equals 5. So for x, I'm going to plug in 1. For y, I'm going to plug in -2. And z, I'm going to solve for. So I get 1 minus 2, which is -1, plus z equals 5. So z equals 5 plus 1, which is 6. So now I see that my single order triple of a solution is going to be the order triple. Remember, always x first, then y, then z. Now we can see that nicely demonstrated here. Here's a graphic showing the three planes, and there's the point of intersection. It's in fact the one that we have, 1, -2, 6. So this actually turned out to be a really nice, simple one to solve. If this hadn't happened, if the y's hadn't simplified and canceled out, we would have had two equations in x and y. Then we would proceed with solving that system of two equations in two variables, and then proceed like before and get z at the end. So the same way, I'm going to leave the check for you. Just plug them in. Plug all three of those, x, y, and z, into all three equations. Make sure that they make all of them true, okay? You can take my word for it for now, but do always check it for your own sake. Let's go ahead and go on so our video doesn't get too long. All right, so here's another one. Always scan the system to see which variable you think would be easy to work with, okay? Now, they all look pretty good actually here, don't they? The coefficients are small, etc. It doesn't matter. So pick your favorite. You know, I am probably gonna go with z again, just because I guess I'm in a z mood. All right. So let's go ahead and name them. One, two, and three. So let's go with the same game plan. We're going to take 1 and 2. Just rewrite them. I know it's some writing, but it's good for you. And then let's go ahead and eliminate. Remember, you got to pick your variable. So we picked z. So we're going to eliminate z from these two. So we're going to go ahead and multiply the bottom equation by -2. So leave the top one alone. The second equation becomes -2x minus 4y minus 2z equals -4, right? So this actually happened to eliminate 2 as well. Now this may not have happened if you had picked a different variable to eliminate, like x or y. So I guess I should be in Vegas right now. I'm having a lucky day. So we get -3y equals -3. So y equals what? 1, right? So I'm going to go ahead and take 2 and 3 and eliminate z as well. So 2 is x plus 2y plus z equals 2. 3 is x minus y minus z is equal to 0. To eliminate z from this one is very easy. Just add them, right? So 2x plus y, 2y minus y is y, equals 2. Now we'll take this 1 and plug it in here. So we get 2x equals 2 minus 1, which is 1. So x equals 1/2, right? Now all we need to do is go to one of these three equations and get our z. Now you may think this may be the simplest equation to go to, but because x is 1/2, I'm actually going to go to the first equation, because 2 times 1/2 will cancel out the fraction. So I get 2 times 1/2 plus y, which is 1, right? Plus 2z equals 1. So we get 1 plus 1 plus 2z is equal to 1. So 2 plus 2z equals 1. So 2z equals negative 1, 1 minus 2. So z equals negative 1/2. So again, you can see this nice system here visualized with these planes, right? And they meet at that point, which is consistent with what we found. So the solution set, which I have graphically verified, is order triple 1/2, x first, and then y, and then z. Now, for your own sake, go ahead and check it. Make sure they all work out just to get some practice. And that's it. That's all you have to do there. Now here we have two equations in three unknowns. Well, these are kind of interesting because basically either maybe they're either going to be like coinciding, right? In which case you would have infinitely many solutions, right? They would basically be the same plane, or they're going to be parallel, which means they never meet. They would never have a point of intersection, right? Or maybe they cross each other like this, in which case they're going to have what? A bunch of solutions. That entire line at the intersection is going to be a solution. So let's see how that gets represented. So basically you either have no solution or infinitely many solutions, right? So let's go ahead and see what happens if we try to solve this system. All right, so remember, you're not going to get to a point where you're just going to get a single solution. So you know it's going to be of infinite format. So the way to approach it is the following. Go ahead and pick a variable that you're going to describe the other variables in terms of. So for example, let's say I pick x, okay? So I want to present my solution as x and then some expression for y in terms of using x, right? And some expression for z, which will also use x, right? So to that end, here's what we're going to do. We're going to go ahead and eliminate, say, y from the two equations, right? Remember, we're going to keep x, so we want to eliminate the others. First, we'll eliminate y, and then we'll eliminate z. So in the first go, we'll go ahead and eliminate y by multiplying the second equation by -3. So we get x minus 3y plus 10z equals 9. In other words, don't do anything to the first equation. The second one becomes -6x plus 3y minus 9z equals -15, right? So now we go ahead and add the two equations. So we get -5x plus z is equal to -6. Now we solve for z and we get z equals 5x minus 6. So we hang on to that. That's going to go here in our solution set for the z part. So we'll go ahead and write our equations again. X minus 3y plus 10z equals 9. 2x minus y plus 3z equals 5. And we're going to multiply the top equation by 3. And we multiply the bottom equation by -10. So on the top we get 3x minus 9y plus 30z equals 27. The bottom equation becomes -20x plus 10y minus 30z equals -50. Now we go ahead and combine the equations, so we get negative 17x plus y, these cancel out, equals negative 23. So we end up with y equals 17x minus 23. So now we have z in terms of x and y in terms of x. We're ready to write our solution set. So it's going to be the order triple x, and then y, which is 17x minus 23, and then z, which is 5x minus 6. And that's how you represent these systems with infinitely many solutions. Similar to the way it was for two equations and two unknowns, right? Of course, we can get additional solutions, actual solutions, by just taking one x value and then finding the corresponding y and z values. I've shown you three such solutions here, like for x equals 1, for x equals 2, and x equals 3. See? If x is 1, for example, you're going to get 17 times 1, which is 17, minus 23, which will give you negative 6. And 5 times 1 is 5, minus 6 is negative 1. Okay? So there is that order triple on the line of intersection. If it's 2, you get 17 times 2, which is 34, minus 23, which is 11. And then 2 times 5 is 10, minus 6 is 4. So there is that point right there. And then the same thing will work for 3, and you'll end up with that order triple. Okay, so that's how you would handle a problem like this. All right, so make sure you understand that, and then we'll move on. All right, here's another system for us to solve. Let's go ahead and scan the variables, right? It looks like y would be the easiest variable to eliminate. So let's start with doing that. So we'll go ahead and call them 1, 2, and 3. Let's go ahead and take 1 and 2 and eliminate y. All right, so we're going to go ahead and multiply the second equation by negative 5. So the first equation we'll leave alone. 5x plus 5y minus 15z equals 9. The second one becomes negative 10x minus 5y plus 5z equals negative 40. So we get negative 5x minus 10z equals negative 31. Okay? Now let's take 2 and 3 and eliminate the same variable, y. This is easy because we can just add, right? So we end up with x plus 2z equals 13, right? So let's call this first one we found over here from the first elimination, equation 4, and we'll call this new one 5. So we're going to take equations 4 and 5 now, which are both in x and z, and solve, or try to solve, for x and z, right? All right, let's go ahead and try to eliminate x. We'll multiply the bottom equation by 5. Leave the top equation alone. All right, so on the bottom we get 5x plus 10z equals 65. When we add them, the left side completely eliminates, leaves us 0. On the right side, we get 1 from 5 is 4, 3 from 6 is 3. 0 equals 34. This is a contradiction. All right, when you're going through the process of solving this through the reasonable method we're using and you hit a contradiction, that means you were trying to do the impossible and find the point of intersection of 3 planes that never meet at one point. So that's when you know this system has no solution. As you go through the steps, if you reach any contradiction, that's the indication of what's happening, okay? So you can obviously see graphically why that's happening, because 2 of our planes are what? Are parallel, all right? And the third one, yeah, does intersect each one, but they don't all meet at a single point, ever. All right, and that's how you handle that. All right, next we're gonna find the equation of a line y equals mx plus b that goes through these 2 points, -2, -40, and 7, -4, but we're gonna handle it a little bit differently than the way we did before by finding the slope and all that. No, we're gonna find it by using a system. Now, because both of these points are going to be on the line, they're both gonna satisfy the equation, right? So substituting -40 for y and -2 for x, I end up with -40 equals -2m plus b, right? And substituting 7 for x and -4 for y, I end up with -4 equals 7m plus b. Now I have a system, right? So all I need to do is solve this system to get my m and b for the line I'm looking for. So I can see I can eliminate b very quickly, right? I'm going to show you a nice trick. You don't always have to add equations. You can also subtract them. So I'm going to subtract the bottom equation from the top. So b minus b cancels out. I get 0, right? -2m minus 7m, that's going to be -9m. I can just not write the 0, right? And on this side, I have -40 minus -4. Just be very careful when you do this, okay? When you subtract, you always have to be more careful, right? So we get what when you subtract? -36. So immediately we get m equals what? 4. And now we can take that 4 and plug it in for m in either equation. I'll just go with this one. So I have -4 equals 7 times 4 plus b. So -4 equals 28 plus b. So I get b equals -32. Now I'm ready to write my equation. Y equals mx plus b, because I have just found m and I have found b, right? So what is m? M is 4. So I get y equals 4x plus b, which is -32, and plus a negative is just minus. So I get 4x minus 32. All right, and that is basically how you handle this. Very different from the way we did it before, right? But it's very effective and it works out nicely. Of course, the previous techniques we've used, whether it's using the slope-intercept form in the different way we used to use it by finding m and b eventually, or using point slope form, etc. It doesn't matter. Using either of those techniques, you'll come up with the same equation as well. So if you want to put it in standard form, you would have -4x plus y equals -32. Multiply both sides by -1. 4x minus y equals 32. So there is the equation of the line in both formats. All right, so here we're going to use a system of equations to find the parabola of the form y equals ax squared plus bx plus c that goes through these 3 points, okay? So basically, we're going to take the 3 points, which are 1, 4, negative 2, 13, and 2, 9, and we're going to substitute it for x and y separately, of course, and get our 3 equations. So for the first one, notice you have 4 is y, so we get 4, okay, equals a times 1 squared plus b times 1, right? We're substituting 1 for x plus c, right? For the second point, we get 13 for y, so 13 equals a times x squared, so a times quantity negative 2 squared plus b times quantity negative 2 plus c. For the third point, we get 9 for y, so 9 equals for x, we're going to plug in 2. So a times 2 squared, I don't need parentheses because it's positive, plus b times 2 plus c. There's our system. Okay, let's clean it up a little bit. And I'm going to put the constants on the other side. Whenever a equals b, right, that implies b equals a, right? This is called the symmetric property of equality. So if I have 4 equals this expression, I can always say this expression equals 4 without having to think about moving one to the other side and changing the signs and all that. I can just use the symmetric property. All right, so I end up with a times 1 squared is just a. B times 1 is just b, so we get a plus b plus c equals 4. And for the second equation, the quantity negative 2 squared is 4, so we get 4a minus 2b plus c equals 13. And our third equation becomes 4a plus 2b plus c equals 9. All right, so there we have a nice system that we can solve to get the a, b, c we need to come up with the equation for this parabola. All right, so just a quick scan tells me C is probably a very nice letter to work with, okay? So I'm going to take the first 2 equations. And I'm going to go ahead and eliminate C, but rather than having to multiply by -1, we'll use the new trick that we found and we'll just subtract the equations. Just be careful when you do that. 1 minus 4, that's -3. So -3a, b minus -2b, that becomes b plus 2b, so plus 3b. C minus c cancels out, equals 4 minus 13, which is -9, okay? Now we'll take these 2 equations and eliminate c as well. So I have 4a minus 2b plus c equals 13. 4a plus 2b plus c equals 9. We're going to subtract the equations again. These cancel out. And we end up with -2b minus 2b, so that's -4b. C's cancel out, equals what? 14. Sorry, 13 minus 9 is 4. 14. I don't know where I came up with that from. All right, so we end up with B equals -1. Okay, that's really nice because now we can use that here to get A. So we have -3A plus 3 times -1 equals -9. So -3A equals -9 plus 3, right? So -3A equals -6. So A should be 2. Now we have A and B. We just plug it into here and get C. So we're going to use A equals 2. B equals -1 to get C. And we'll use it here, right? So 2 plus -1 plus C equals 4. That's 2 minus 1 is 1. 1 plus C equals 4. So C equals what? 3. So now we have A, B, and C, right? Here's A down here. Here's B. Here's C. So we're ready to write our equation. So we get y equals A, which is 2. 2x squared plus B, which is -1. Plus or minus becomes minus. So minus 1x is just minus x. And then plus C, which is plus 3. There you go. There's our equation. And that's how you handle that problem. Okay? Let's go ahead and try another. All right, here's the last problem we're going to look at. An investment of $63,000 was made by a business club. The investment was split into 3 parts and lasted for 1 year. The first part of the investment earned 8% interest, the second 6%, and the third 9%. The total interest from the investments was $5,130. The interest from the first investment was 5 times the interest from the second, and we want to find the amounts of the 3 parts of the investment. So remember, this is a simple interest scenario. So the 3 investments, basically for the first, the formula at work is going to be principal times rate times time equals interest, right? So for the investment 1, we're going to get, because it was split into 3 ways, so let's say let X be amount of investment 1, Y be the amount of investment 2, and Z be the amount of investment 3. So when we want to calculate the investment 1 interest, we're just going to take the principal X, right, multiply it by the rate, which was 8%, by 1, which is the time, right, 1 year. So we're going to get I1 equals X times 0.08 times 1, which is just 0.08x. The interest from the second interest is going to be Y times 6%, so 0.06 for 1 year. So we're going to get 0.06y. And the investment from the interest from the third investment is going to be the principal Z times 9% times 1 for the year, right? And we end up with 0.09z. So now we can set up our system. We know that the total amount of the investment was 63,000. So X plus Y plus Z equals 63,000, right? We know that the total interest that they earned was 5,130. So if we add these 3 interests from the different investments, the 0.08x plus 0.06y plus 0.09z, we should be able to get our total interest, which is 5,130. And we know that the interest from the first investment, that means I1, which is 0.08x, was 5 times the interest from the second. So I2, so 5 times 0.06 y. Okay, so that's what we know. That is basically where our system comes from. All right, so now all we need to do is make it simpler by getting rid of the decimals. So the first equation is nice and simple, we keep it. And for the second one, we'll multiply both sides of this equation by 100. That's going to clear all those decimals. I'm going to get 8x plus 6y plus 9z is equal to 5130, and then add 2 zeros. Remember, you got to multiply both sides, so we get 513,000. For the third one, we have, this is already 0.08x equals 5 times 0.06, which is 0.3, so 0.3y. So I'm going to multiply both sides by 100, and actually let's get them on the same side, that'll be nicer. 0.08x minus 0.3y equals 0. Now we'll multiply both sides by 100. So we get 8x minus 30y equals 0. Okay, so there's our simplified system. Okay, so we notice that this last equation doesn't have any z in it. So if we can eliminate z from these two as well, then we'll have a system of two equations in two unknowns in basically x and y. So let's do that. So let's go ahead and eliminate z from 1 and 2. I can just multiply the first equation by -9. So we get -9x minus 9y minus 9z equals, we need to multiply -9 by 63,000. So we get -567,000. The second equation we do not change. All right, we'll add the equations now. We get -x minus 3y, z's cancel out, equals, now we add the 513,000. So we end up with -54,000. I notice I can divide both sides by -1 and get x plus 3y equals 54,000. And now we go to this other equation, which is in x and y. I notice I can make it simpler by dividing both sides by 2. So I get 4x minus 15y equals 0. So now we have 4x minus 15y equals 0, and x plus 3y equals 54,000. We can quickly solve this by multiplying the bottom equation by -4. So we leave the top equation alone. 4x minus 15y equals 0. So we get -4x minus 12y equals, we need to multiply 54,000 by -4. So we get -216,000. So now we add the equations, so we get negative 2 and 27y equals negative 216,000. So we'll go ahead and divide negative 216,000 by negative 27. And we end up with y equals 8,000. Now we can get x quickly by substituting this y value in here. So we get x plus 3 times 8,000 equals 54,000. So that's going to be x plus 24,000 equals 54,000. So 54,000 minus 24,000, which should be 30,000, right? So x is 30,000. So now to get z, all we do is plug in, that's 30,000. We plug in 30,000 for x and plug in 8,000 for y into the first equation right here, and that'll give us z. So z is going to be basically 63,000 take away 30,000 take away 8,000, so 25,000. All right, so now we know that the amount for investment 1 was, so amount 1 was X, which is $30,000. The second amount for investment 2 was Y, which was $8,000. And the final amount for investment 3 was $25,000. All right, so with these, as you can see, they're not necessarily difficult, right? This is where you have to understand the difference between difficult and tedious. These are tedious. There's a lot of detail. You have to be very careful about the details. A minor little sign error somewhere and it can go wrong, right? So, but keep, think about the bright side. They're not difficult, right? But you do have to be very, very careful with these, okay? And that pretty much brings us to the end of this lecture. So take care until our next one.